So let's continue to move up in complexity to the other tetrapods. Concept 34.6 says amniotes are tetrapods that have a terrestrial adapted egg. This was a big step. As we know, amphibians are tetrapods and they are terrestrial creatures, but they're still tied to the water for reproductive purposes. Well, we have a new set of creatures now called amniotes. Amniotes are a group of tetrapods whose living members, the extant members, include reptiles, including the birds, and mammals. And they are called amniotes because they have a terrestrial adapted egg. So some of these creatures, like reptiles and birds, they still lay the egg outside of the body, but it has a shell, either a leathery shell or a hard shell, that basically protects the developing embryo inside. In the case of mammals, the egg and the embryo develop inside the mother, nourished by the mother. So it's an internal growth process. But these would still all be considered amniotes. If we wanted to look at sort of the family tree or the phylogeny of amniotes, it would include many creatures that are no longer around, many creatures that are extinct, including a lot of the dinosaurs. There are only one lineage of that still alive, and that would be the modern day birds that you see. We have crocodilians, which would be a fairly basal group going pretty far back with the crocodiles and the alligators. Turtles, you notice the dotted line, we're still not sure exactly how they fit in. And then of course we get down here to some of the living creatures, like this little living guy here, the tuatras, I believe is how it's pronounced, and then of course we have the mammals as well. So a lot of these guys are no longer around, but they are part of the lineage of the amniotes. The derived characters of the amniotes would probably be easy to guess based on the name. The amniotes are named for the major derived character of the clade, which would be the amniotic egg, which contains membranes that protect the embryo. And the extra embryonic membranes are what we call the different parts of the egg are the amnion, the chorion, the yolk sac, and the allantois. That last word might be allantois. So the amnion, the chorion, the yolk sac, and the allantois or allantois. I'm not sure. I'd have to check on that one. So here's an egg, an amniotic egg. You can look on textbook page 714 for more details. This could be anything from an alligator egg to a chicken egg. It doesn't really matter because they all have very similar parts. They have what's called an extra embryonic membrane, or they have various extra embryonic membrane. Wow, say that 5 times fast. And that would include this amnion, the allantois, the chorion, and the yolk sac that all kind of surrounds this creature. It provides protection. It also allows for development of the embryo. Basically what you have is a pond within the egg, and so the egg develops still in sort of an aquatic environment, but that aquatic environment is contained within the egg. So no longer does the creature have to go back to the pond or the water to lay its eggs. It can do so on the land because it has this amniotic egg. The amniotic eggs in most reptiles and some mammals have a shell. There's only a few mammals that still lay eggs. Most of them develop internally, but there are a few. And they have some sort of shell that's either going to be leathery, like turtles. A lot of reptiles tend to lay sort of leathery eggs, or they have a hard outer covering like most birds. This amniotic egg was a key adaptation that allowed for terrestrial living. I mean, this basically broke the chains of having to go back to the water or live in the water to reproduce. So this allowed the tetrapod embryo again to develop in its own little private swimming pool, its own little aquatic environment within the egg, and it also helped protect that developing embryo from the environment and from creatures that might kill it and eat it and that type of thing. Amniotes have other terrestrial adaptations as well. Again, the further up onto the land these creatures went, the more various adaptations they had to have to survive, such as impermeable skin, as opposed to, say, the amphibians that have kind of thin, permeable skin. The creatures that live further up on the land away from the water, they need thicker, more or less permeable skin to hold in moisture and to withstand the elements. They also have the ability to use their rib cage to kind of expand the rib cage in and out to help bring air into the lungs and ventilate their lungs. A couple of different creatures we want to look at, some early amniotes. The current living amphibians and amniotes split apart from each other at their common ancestor about 350 million years ago. Early amniotes were more tolerant of dry conditions than the early tetrapods. So as we continue to move on to the land, again, there were various adaptations that were necessary for life. And the earliest amniotes were small predators with sharp teeth and long jaws. And here's an artist's conception of what one of these little guys would have looked like, very similar to some of the common reptiles that we have now. So we're down to the amniotes, which would be reptilia. That would be your reptiles and your birds, and then of course that would also include mammalia, which we're going to get to last. So the reptiles include the tuatara, the lizards, snakes, turtles, crocodilians, birds, and some extinct groups. The reptiles oftentimes have scales that create a waterproof barrier, again, to hold that moisture in dry conditions. And most reptiles lay shelled eggs on land, although there are a few reptiles that have live birth. So here's a good example of a type of snake that lays its eggs. There's some little baby snakes that are hatching out, and that egg protects them from the external environment. Most reptiles, such as snakes and lizards, are ectothermic. We would, in the olden days, we might have called that cold-blooded. It doesn't mean that their body temperature is necessarily much colder than other creatures, but it just means that they use external heat sources as one of the primary methods of keeping their body warm. They absorb external heat instead of being able to create large amounts internally. They can create some internal heat, but they kind of save their own energy by laying in the sun and absorbing that type of heat from warm rocks and warm concrete and that type of thing. So they're ectothermic, which means they get their heat from outside, ecto meaning external or outside. Birds, which are also part of this reptilian group, belong to the same clade. They are endothermic, like mammals. They create their own internal heat so they can keep a more steady body temperature. They're capable of keeping their body at a more steady, warm temperature, and that is because of their increased metabolism. And we would call that warm-blooded. So reptiles tend to be cold-blooded. Birds, which actually are part of the reptile group, would be warm-blooded, and mammals are warm-blooded as well. The oldest reptilian fossils date back to the Carboniferous period. If you'll remember, that was when we had these giant ferns and some of the non-seeded type plants that eventually became a lot of the coal deposits that we use today. The first major group to emerge were the parareptiles, which were mostly large, stocky, quadrupedal herbivores. And then as the parareptiles were dwindling, the diapsids were diversifying. And the diapsids were the group that eventually led to the two main lineages called the Lepidosaurus and the Archosaurus. The archosaurs. The lepidosaurs include tuataras, lizards, snakes, and some extinct creatures. The archosaurs produced the crocodilians, some other extinct creatures, including the dinosaurs. From this group of tetrapods, from the various reptilian groups of tetrapods, we had the first creatures that were able to exhibit flight. We had the pterosaurs, which were the first tetrapods to exhibit flight. And of course we have the dinosaurs, which diversified into a huge, vast range of shapes and sizes, basically ruled the earth for millions of years. And they included bipedal carnivores that were called theropods, which would include groups like the T-Rex and some of the other bipedal dinosaurs that you think of, Allosaurus and Tyrannosaurus rex. This is also the group, the theropods, from which the birds descended. So the birds are the last living remains of the dinosaur lineage. There's still a lot of cool debate going on about dinosaurs, whether they were endothermic or ectothermic. When I was a kid, most people would have told you that dinosaurs were kind of slow, sluggish. They were going to be cold-blooded, ectothermic creatures. But we have developed evidence in the last 30 or 40 years especially that kind of suggests otherwise. There's a lot of fossil evidence that seems to show that a lot of these dinosaurs may have been a lot more agile and fast-moving, perhaps even endothermic, and that they took care of their young, and they not only set on nests but then kind of helped raise those young, and that's kind of against what we used to think about them. So there's still a lot of debate going on, and of course as we gather more information we'll kind of understand more, and dinosaurs are a fascinating topic, so that's never going to go away. But the way we see them has changed, especially in the last, say, 20 or 30 years. As we've already discussed, the vast majority of the dinosaurs, with the exception of the lineage that led to the birds, became extinct by the end of the Cretaceous period. A couple of different reasons for that. One of the main reasons may have been partially caused by an asteroid that we talked about earlier, the crater that struck near Mexico, sort of in the Gulf of Mexico area here, and that crater, that meteor asteroid impact, may have caused some huge environmental changes that led to the extinction of the dinosaurs. It probably wasn't just that one thing, but it was probably a number of factors. But this impact, this crater, was probably one of the major reasons that caused the dinosaurs to eventually go extinct. We mentioned the two groups that came out, the two main lineages, the Lepidosaurs and the Archosaurs. So let's go to the Lepidosaurs. There's only one surviving lineage of the Lepidosaurs around, and that is represented by two sort of lizard-like creatures called Tuatara, and there he is right there. He kind of looks like an iguana, but he's got a slightly different lineage. And the other major living lineage of Lepidosaurs consists of squamates, the lizards and the snakes. So the lizards are the most numerous and diverse reptiles apart from the birds. There are more different kinds of lizards than pretty much any other kind of reptile, except if you include the birds in that grouping, as you should. So all different sorts of lizards here. We have the Tuatara. Back it up. We have the Tuatara, which is slightly different, and then we have all these different types of lizards and snakes and creatures, all in the reptile grouping. Here's a little thorny devil lizard, snakes, pit vipers, turtles, alligators, all kind of belonging in this area. So snakes, we know, are legless lepidosaurs that evolved from lizards. They at one time had legs, and in some snakes you can still find vestigial legs. Snakes, for the most part, are carnivores, and some are also venomous. So we know that some snakes have developed poison that they can use to either defend themselves with or attack and hunt and kill prey. We do have some videos showing a couple different of these creatures, marine iguana from the Galapagos, snakes, and that type of thing. So again, check in the folder for this particular chapter to find those videos. Another grouping of reptiles you're probably familiar with would be the turtles. All turtles have a box-like shell made up of upper and lower shields that are fused to their backbone, fused to their vertebrae, their clavicle, and their ribs. So they kind of have this fused shell that is connected to both their dorsal and ventral bones, the skeletal system in both their front and their back. Some turtles have adapted to deserts. You can find tortoises that live in desert conditions with very little water, and some entirely live their lives still in ponds and rivers, and some even still in the oceans. So you have a wide variety of turtles. They have very similar kind of body morphology, but they can look quite different because of their different environments. So another good example of a reptile. Not quite sure where they fit in exactly with the phylogeny. We're still working on that. Alligators and crocodiles, these guys are sort of like living fossils. They are a very basal group. They haven't changed much in millions of years. The crocodilians belong to the Archosaur lineage that dates all the way back to the late Triassic. So you can look at them and you can say, my gosh, that does look kind of like a dinosaur or a creature that's been around for quite some time. Birds also belong in this group. A lot of people don't think that that's the case, but birds are a part of this lineage of the reptiles. They are the last remaining vestige of the dinosaur lineage. They are archosaurs, but almost every single one of their features has been heavily modified for flight. So a lot of their reptilian anatomy is hardly visible because everything about them has really gone toward increasing their adaptation to flight. So making them lighter or smaller or better able to fly is what pretty much all their adaptations, or most of their adaptations, are about. Some of the derived characters of birds all again have to do with flight. So major adaptations to the wings would be the feathers, of course, the existence of these feathers that are made out of keratin, a similar material that makes up your fingernails and your hair. Other adaptations include the lack of a urinary bladder, females with only one ovary instead of two, small gonads, loss of teeth. You'll notice most of these adaptations have to do with decreasing weight, increasing aerodynamics, all having to do with that adaptation of flight. So here you have like the bone structure of most birds is very hollow bones, very lightweight, still strong because they have this network of bone material inside, but the bone structure of birds tends to be very hollow, and the skeleton system of a bird is very much lightweight as compared to, say, a similar creature that does not fly. And then of course we have the feathers. If you were to zoom in on a feather, it is like a very heavily modified type of hair made out of the same sort of keratin material. All of these adaptations to help it achieve this flight ability. As you can imagine, the ability to fly is a tremendous advantage, and you can see how that has helped birds, and you can see there's such a huge variety of birds, and they have become well adapted to a wide variety of environments, taking advantage of this characteristic of flight. Flight enhances their ability to hunt and scavenge, their ability to escape from terrestrial predators. It allows them to migrate over huge distances, but the downside is it requires certain things of them. It requires a huge expenditure of energy, so they have to have a high metabolism. It requires very acute vision, fine muscle control, and these are some of the characteristics that you see in most birds. The origin of birds, they probably descended from a small theropod, which would be one of the creatures we talked about, the early small carnivorous dinosaurs. Early feathers might have evolved not necessarily for flight. A lot of scientists think that feathers, when they first began to develop, they weren't necessarily for flight, that they were sort of co-opted for that reason later on. Early feathers, because they wouldn't have been fully feathered, most likely they developed small amounts of feathers over time, they probably evolved for insulation, camouflage, courtship displays, and then later on these feathers were kind of co-opted for this purpose of flight. Early feathers might have helped dinosaurs in a couple different ways, not necessarily by flying through the air, but by helping them gain a little bit of lift, and when they jumped, gaining traction when running up hills, kind of flapping these sort of simple sort of wings, gliding from tree to tree, not necessarily powered flight, but simply kind of a softer landing going from tree to tree. About 150 million years ago, feathered theropods began to evolve into what you would basically call birds. Archaeopteryx is probably the best well known. It remains the oldest bird known for which we have direct fossil evidence. Here's an artist's conception of Archaeopteryx, the earliest known bird. It had a lot of characteristics of modern birds, but it also had some characteristics of reptiles. So it had a toothed beak. Most birds no longer have teeth. It had wing claws. Most birds, no longer have claws on the tips of their wings. And it had a long tail with many vertebrae, which that's not necessarily the case for most birds today also. So it was kind of a combination of modern bird and reptile. And this would be the Archaeopteryx, an early form of birds, the last lineage of the dinosaurs. When we get to the extant or the living birds belong to a particular clade, and there are several different kinds of living birds. Some of them are flightless, the ratites, such as the emu and the ostrich and the penguins. These guys are a little bit more rare because most birds have the ability to fly, but there are certain species, types of ducks and pigeons, as well as these large birds like emu and ostriches that cannot fly or do not fly. They're more adapted for a terrestrial habitat. So the emu and the ostrich, you notice, have these huge, enormously powerful legs, and they're well adapted for life on sort of the savanna or the grasslands. And then of course we have penguins, which are well adapted to a different kind of flight, to flight underneath the water and swimming in the oceans. The demands of flight have basically meant that most birds kind of have the same sort of shape and form. If you're going to be good at flight, it's helpful to have a certain shape and form. So most birds tend to follow a certain pattern, but they do vary from one another in their profile and the various colors, their behavior, the shape of their beaks, the shape of their feet. That's all different adaptations they've developed for their particular habitat. So we have a couple of videos in here of hawks and swans. You have a wide variety of birds. I mean, it's amazing to look at the variety of birds, from hummingbirds to hawks to flamingos. So here you have a bird that's capable, because of its bone structure, of flying backwards and hovering in place. It also has a very well adapted beak, heavily modified beak for getting nectar out of the flowers. Here you have another specialized beak in the flamingo, who searches through the mud for small crustaceans and shrimp and the like. Well adapted feet. Different birds have different styles of feet for perching or wading or swimming. So there's still quite a bit of variety in beak shape, coloration. Even though a lot of birds have the same basic body style, there's still tremendous amounts of evolution going on in natural selection for the different habitat. We're going to stop right there. So that's the reptiles. That would include everybody from the crocodiles, the turtles, to the birds, and we're finally going to get to the mammals, which would be my group, our group, your dog's group, and that's coming up next. We'll be right back.